Share screen. Yeah. Can you see this example 3?
Yep.
Okay. Let me read the question very quickly. Water is to be pumped by using two pumps, pump 1 and pump 2, from reservoir A to reservoir B. Pump characteristics and pipe information are given below. So these are pump characteristics. These are the information related to the question. We have viscosity, total length of the pipe, diameter of the pipe, F value, and pump heads for pump 1 and pump 2 for different discharge values given to us. The questions asks us to decide the operating discharge and the pump head for these things. For the part A, if the pump 1 works alone. For the part B, if the pump 2 works alone. Part C, if pump 1 and pump 2 works together as series. And part D, pump 1 and pump 2 works together as parallel. So what is different in this question from the previous one is this time we don't have a pump equation provided to us. We don't have a pump equation given by the question. Last time, if you remember, we had something like H available is equal to H0 minus A times something. We had something like that. This time, we don't have any extra equation. So we will have only one equation, and that will come from the energy equation between point A and point B. And since we don't have the second equation, we will need to draw a graph by using these values. So for example, what we will do is we know, so we will say when the discharge is 0, the head is 70. When the discharge is 100 liters, the head will be 68 meters, and it will go like this. And from the equation that we are going to derive from this energy equation, we will put these same discharge values and we will get the pump head values for these same discharges, and we will draw these two into the same graph. And when they coincide, the point that they coincide will be our operating point, and we can read our operating discharge and pump head. This is the procedure. So let's start with the pump 1 part A. So we will make pump 1 work alone. So as I said, first of all, we need to write energy equation between point A and point B. So total head at point A minus the head losses, major and minor, plus the pump head will be equal to total head at point B. In this question, I forgot to write here. It says ignore the minor head losses. So we don't have any minor head loss. Again, the question says ignore the minor head loss. Okay, so we don't have any minor head loss. We have only major head loss. And its formula here, FLV square divided by D2G. So for the point A, again, we are dealing with two large reservoirs. So for point A and point B, we can set their pressure heads and velocity heads into 0. So we can cancel for both points, pressure head and velocity head. Pressure head and velocity heads are 0. So what do we left with? We left with the elevation head at point A minus the major head loss plus the pump head will be equal to the elevation head at point B. So I want to write an equation for the pump head, right? So I leave this pump head thing alone and throw this elevation head at point A and major head loss thing to other side of the equation. So what do we get? Pump head will be equal to elevation at point B minus the elevation at point A. I took them into parentheses. You don't have to, but it makes me see easier. And plus the major head loss. So in this question, there is no velocity value given to us, but as I said, we will put these discharge values into this equation to see what is the head at pump coming from this equation for these same discharges. So instead of velocity value, I write discharge divided by the cross-section area. So when I put this thing in terms of velocity, we get this equation. So it's time to put the values that we know into this equation. What do we know? We had the elevation at point B and elevation at point A. It was 70 and 20. We know the F value given by the question, 0.03. And we know the pipe diameter, 0.5, and the length of the pipe, which was 1,500. So you put F, L, D. We don't know Q. I mean, we know, but we will put one by one, and we will get different values for different discharges. So we will keep it as Q. And for the A value, of course, it is the cross-section area of the diameter. So what is the cross-section area? Pi d square over 4. This d is the diameter. So you put the diameter value here, and this g is the gravitational acceleration, which is the 9.81. So after you put everything and do this calculation for this pump head, you'll get a formula like this: 50 coming from here, 50 plus, and this corresponds to 118.98 Q square. Okay, so this was our aim. We got this equation. Now we will use this equation for all, I mean not all, but for part A and B when we make pumps work single. So we will accept this as our system equation. So for the part A, it wants us to check when pump 1 works alone. So what are our discharge values? 0, 100 liters, 200 liters, 300 liters, and 400 liters. You need to put them, by the way, in terms of meter cube per second, because our head is in terms of meter. So you need to be careful about it. These discharges are given us as liter per second. So you need to convert these values into meter cube per second. And when you convert from liter to meter cube, you need to divide with 1,000, or you can say 10 to the minus 3. You will multiply, of course, that time. So when you put these values, I put them here. I put 3 of them as an example, so you can see how I did it. So for the first one, the discharge is 0. You can see it. So when the discharge is 0, its system will be equal to 50 plus this one times 0 squared, so it will 50. When the discharge is 100 liters means 0 liters per second. Okay. When the discharge is 100 liters per second means 0.1 meter cube per second. So you bring it and put it here into this equation, and you get 51.2 meters as a pump head. And you will do it for 5 of them. And the values are given here. I calculated and put them here. You go like 50, 50.1, 54.8, 60.7, and 69.1. And what was our discharge pump heads for pump 1 for these discharges? I wrote them here as well. It was like 70, 68, 61, 48, and 36. So I wrote them here. So you will draw a graph which will show the pump head on the y-axis and the discharge values on the x-axis. So for the pump 1, when discharge is 0, head is 70. When discharge is 0.1, head is 68. 0.2, head is 61. It goes like this. Of course, since I draw it by hand, it's not that accurate, but you get the point. You get the idea. It is the important one. And for the system 1, again, for 0, it's 50. For 0.1, it's 51. Blah, blah, blah. It goes like this. And as I said, when the point that they coincide, this curve and this curve, the point that they coincide, we accept as our operating point. So let me get a bit closer so you can see it easier. Of course, I decided these points by myself. So this is by eye, I'm deciding by eye. So since it is a bit close to the left side, I thought this one is 0.22 meter cube per second as a discharge. And as a head, since it is a bit close to the 60, I thought it's, I said like, let's make it as 57 meters. This is for the first pump. Did you understand everything till now? Or if you have any questions, ask me now about this part A.
Hocam, can you just briefly explain that table over there?
Which table?
Discharge, head pump, and
This one.
no, the one next to the graph.
This one.
At 70, 68, 61. Where
This
those
one.
came
Okay,
from?
okay,
Yeah.
okay, 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 okay. Okay. For the first column and the second column, you can see their names as well. Discharge and HP1, which means pump head for the pump 1. I took these values directly from the given values by the question.
Okay. Thank you. I get it now.
And these are I calculated them by using this equation, okay? That we derived by using energy equation.
Okay, thank you.
Okay, no problem. So for pump 2, I mean part 2, now instead of pump 1, we will make pump 2 work alone. Same procedure. And as I said, we've driven this system equation from energy equation. So we can use it for pump 2 as well. That doesn't matter, okay? So we will...
Hocam,
Yes.
Hocam, in the graph, in the first graph, where's the 70, that first line? Where's the 70?
Here.
Yeah, that one. Where's it came from? Can you please explain?
Okay. It comes from here.
It's already given.
Yes.
Okay.
Okay.
And the second one that we calculated.
Yes, this curve is given by the question. This one, the one that is going down. Okay.
Tamam, thank you.
Going up, we are calculating it. Okay.
All right, thank you.
No problem. So for the part B, when the pump 2 works alone, same procedure, exactly the same procedure. Nothing is different. But since we already calculated this system equation for the pump head, we don't need to calculate it again. We will use this equation. And since we are going to put same discharges, again, we will get same values for pump 2, for part 2 as well as a system. What is going to change is these pump head values coming from the question will change. We will put pump 2 values here. This and this won't change. You can see it because we are using the same equation and we get these values from the equation that we derived. So, and we are using same discharges. So again, we will put 0 and we will get 50. We will put 0.1 again, we will get 51.2. But the thing, these values will change because this time we are using pump 2. So let's check. Let me show you. I wrote here 40, 38, 35, 27, and 15 for 0, 0.1, 0.2. These are meter cube per second. Here, question gave us as liter per second. This is why it is 100 here, but at the down, in the below, it's 0.1. And if you see, if you look at this pump D values, 40, 38, 35, 27, and 15. So I bring these values for this much discharges and directly put it here, okay? And these came from equation, as I said, since we are using same discharge values and same equation that we driven from the energy equation, the numbers, the values are same. So what is the next step? You will form our graph, discharge, pump head. By the way, write the names of these axes because it's important. I made a mistake here. Don't be like me, write their names. So put discharge here and its unit, put pump head here and its unit. So for the system, it starts with 50, 51.2, 54 point something, 60 point something, and 61 point something. And what was the pump 2 characteristics, the values for this much discharges? It starts with 40 when the discharge is 0, 40, 38, 35, 27, and 15. So if you remember, in the first part, they were coinciding, and we accepted this point as our operating point, okay? And we said our discharge is this much, and our pump head will be this much. But this time, they are not coinciding, so we don't have any operating point, so we will say pump 2 is not suitable for this system to be work alone, okay? So did you got this part B as well? Any questions?
Yes, hocam.
Okay. Now, part C. What part C wants us to do? Part C says pump 1 and pump 2 work together as series. Okay. The thing you need to know is when two pumps work as series, they use the same, the discharge value doesn't change. Because if pump, let's say pump 1 is here and we put pump 2 is here, okay, as series. So we are using the same discharge coming from the same pipe. The same flow goes through pump 1 and pump 2. So the discharge value doesn't change. What changes this time, since we put two pumps, we add their heads together. So what I mean is, this time for 0 discharge, as a combined pump head, we will have 70 plus 40, which means 110. So let me show you what I mean. So here, again, as I said, the discharge values won't change because the water flows through pump 1, then through pump 2. So it's the same amount of water, okay? Discharge value doesn't change, but since we have two pumps this time, their heads will add together. However, the system equation is still same because the system equation never changes, okay? Because you derive it from energy equation. So it won't change. So you will still have the same values. Okay, I went too much down. You will have same values or same discharge values. Okay.
Hocam,
yes.
if you are having two identical pumps, hocam, and they are connected in series, is the system equation going also to be remain the same? Isn't going to be like divided by 2?
No, no. It will stay same. This one will stay same, and this one, since they're identical, you can directly double it.
I mean, like when we write the energy equation, we will add two pumps, so it will be 2 HP, and in one side. Shouldn't we like divide by 2 the whole equation, or no need for that?
Can you explain again what you mean, the second part?
I mean, Hujam, when we write the equation, energy equation between two reservoirs in this equation, in this example, for example.
Yeah, this one you mean here.
Yeah, so HP instead of 1 HP, it will be 2 HP, right, Hujam?
Yeah, but
if two identical pumps are in series.
Yes, you can. I mean, if the question directly asks you, like, let's say the question gave you this one and told you make pump 1 and pump 2 work series, and it gave you the pump heads. Okay, you will write here pump 1 head plus pump 2 head. But in this question, it's a bit different. We have different cases, and we are writing this is like this stands for everything. I mean, this stands for when they work together or when they work alone. So we keep it like as it is in this one.
Yes, yes, I understand. Thank you.
Okay, no problem. So where was I? Okay, I'm here. So okay, what I said the discharge won't change. Is since the discharge is not changing and we are using the same system equation, these values won't change, but the only difference is coming from here. Since we are using pump 1 and pump 2 as series, we will add them together, their heads, of course, for the same discharge value, and we will sum them and we will get these values. Show me as an example. For example, for 200 liters per second, 200 liters per second means 0.2 meter cube per second. Okay, what is the head of pump 1? It's 61. What is the head of pump 2? It's 35. So in my table, you can see for 0.2 meter cube per second, I added 61 with 35 and I got 96. It is same for all the discharge values. Okay, you add pump 1 and pump 2 heads together. So what is the next step? We will draw the graph, of course. Again, don't forget to write your names of the axes. This is discharge in terms of meter cube per second, and this is the pump head in terms of meter. So my system is this one, again, 50, 51.2, blah, blah. It goes like this. And this is the curve coming from the combination of pump 1 and pump 2 heads, 110, 106, 96, 75, and 55. They coincide somewhere right here. So yeah, again, by eye, I said this is 0.34. I mean, you can say it's 0.35. It doesn't that much because you're reading by your eye. So it's not that important. And this is what I wrote, 64. Yes. And we decided it's 64 meters. So, I mean, as I said, this coinciding point is our operating discharge and our operating pump head value. This was part C. Any questions related with this part? Okay. Then part D. When pump 1 and pump 2 works together as parallel. In this question, as you see, we are not using identical pumps. And when you don't use identical pumps, it's actually not suggested. It's not like it's not suggested, but it requires some complex calculations, and those calculations are not in the scope of this course. So you don't learn how to calculate to run two different characteristic pumps as a parallel. So actually this part D is not related with you, but let me show what happens. At least I'm not gonna waste your time, but let me show you very briefly. So once you draw this graph after the calculations, okay, you get this for first pump, second pump, and the third pump. Sorry, for the system. The system is changing now because, as you know, when two pumps were together as parallel, the discharge doubles itself. The discharge is increasing this time. So system curves of course, since the discharge is changing, the values for system curve is changing as well. But the problem is this thing only coincides with this one, but doesn't coincide with the first pump. So like it requires complex calculations. You can say here it is not suggested. Yes, since they are not, since they don't have the same characteristics. Yeah. So this was the part D. If they have the same characteristics, of course, you need to run the calculations. Okay, this is the example 3.
Hocam, can you go to system equation where you derive it?
Okay. I draw it. I did it. Okay, here.
Yes,
How I
yes.
did it?
Can you go down a bit?
How?
I'm just trying to get the formula from Q, that 118 part.
This one.
Yes.
Okay, it comes from here. We had FLD times, this is velocity normally. Okay, instead of velocity, I put discharge divided by cross-section area because discharge is velocity times cross-section area. So I made a reverse calculation there. And 2G, I put the values coming from the question. This F is given as 0.03, L is given as 1500. The diameter of pipe is given 0.5. I keep the Q as it is because we would use it for different discharge values. And for this A, it is the cross-section area of the pipe, which means pi d square over 4.
Yes, hocam, I get it. I did a calculation mistake. That's why it
Okay.
was wrong. Thank you.
Okay, no problem. So another question?
Hocam, we are not responsible from part D, right?
Yes, you won't have a question like this. I mean, they won't ask you to calculate for two different characteristics pumps when they run as parallel. They won't ask you any question like that.
Okay, thank you.
No problem. So I will stop here. If you don't have any questions, of course. If you have any question. Okay.